Hello, my name is Todd Greenberg, and this is my presentation on blockchain solutions for IoT security. So first, what is IoT? IoT, which stands for Internet of Things, describes objects and devices that collect actionable data from users. So some examples that I included here are smart homes, which can communicate with other entities outside of the house. Others are the Eddystone Beacon, which communicate with users via Bluetooth and connect to their phones. And another are smart shelves, which can actually sense the types of people that are interacting with the objects on the shelves. The real power of IoT is shown when multiple devices work together. So for instance, in the case of smart shelves can actually communicate with workers in the back to determine when inventory is low. So given that 5G is becoming more and more widespread, this will give way to more IoT implementations. So this brings up some issues in regards to security in IoT. One of them is that the devices currently have limited computational power, which bars the devices from using things like firewalls. Standardization has not been developed for IoT. As well, given that IoT has a lot of devices that communicate with one another, there's a wide attack area. And given that IoT is moving into spaces like healthcare, finance, and transit, security is becoming more and more important. And blockchain has been proposed as a solution for these security issues. Which brings us to our next topic. What is blockchain? So blockchain can be described by using this very famous computer science allegory, which is known as the Byzantine generals problem. And the allegory describes a situation where, let's say, there is a group of generals led by a commander planning to storm a fortress. In order for the plan to go correctly, everyone has to be on the same page. But then let's say there is a traitor or multiple traitors within the group. The traitor can be one of the lieutenants, or the traitor could be the commander himself. And the plan of the traitor is to give faulty messages to other lieutenants to cause miscommunication and cause the plan to fail. So this allegory describes distributed systems working together, where let's say one distributed system is not working properly and then therefore sends instructions to other servers to work improperly as well. The thinkers behind this allegory proved that given M traitors, you need 3M plus 1 generals with the correct information. Meaning you need at least one more than 2/3 of the nodes to have the correct information to defend against faulty nodes. But if there were only 3 generals, it's either all or nothing. You either have all 3 working in tandem or the system falls apart, because you either have everyone on the same page or no one on the same page, because 2/3 is not enough to fill the requirement. So which brings up the question, is there a solution for 3 generals or 3 nodes? And the paper says, yes, there is. And the solution is to use verifiable signatures. So tying back to the allegory, the general that wants to send out the message signs the message and copies it and sends it to all the other generals. And the other generals verify that the signature is true, copies it, and then sends it all to the other generals, and the other generals do the same. So in this case, all the nodes can verify that the signature is real, and if the signature is forged, it's rejected. And this solution created the inspiration for blockchain. So the reason why blockchain fulfills the requirements of this Byzantine generals allegory is because it's decentralized. There's no singular owner of the information. The data itself is immutable, so therefore you can't change it. And also it's redundant, just like how the generals send the messages and copy it to all the other generals. The nodes also copy the data and have all the data within their own system. And therefore the data is redundant and there's no one single point of failure. So now we're going to talk about the actual data structure of blockchain, which can be represented by this picture. So essentially, blockchain can be likened to a linked list where you have one block which has the hash, which is a one-way hash, essentially an encryption of the data that's within the block. And it also has a reference to the previous hash, which is therefore the next block. And then then that block has the hash of the previous block, and so on and so forth. So how the blockchain is built is that nodes essentially compete with one another to solve the hashing algorithm used to create the hash on the current block. And given that this is a one-way hash, essentially the way the nodes figure out the algorithm is essentially by brute force. So when one node guesses the hash correctly, a proof of work is created where all the nodes in the system verify that indeed that node did create the correct hashing algorithm. So then that node has the responsibility of creating the next block and then creating the next hash, and then all the other nodes guess which algorithm that node used, and then that continues the cycle. So here are the security benefits of blockchain. The main security feature is the fact that there is a proof of work. So like how all the generals in the allegory can verify the signature, all the nodes can verify that indeed that one node solved the hashing algorithm properly. And given that all the nodes can have a chance to create the next block, it's decentralized. There's no one singular owner. As well, each node has a copy of the blockchain, which is where the redundancy is implemented, which lowers the risk of data manipulation. So if one person was able to create a faulty block on one node, it would be rejected by all other nodes. As well, blockchain protects against a 51% attack, where a malicious actor somehow creates enough nodes that take over 51% of the network, which therefore tilts the balance of power in that person's favor. The reason why a 51% attack is highly unlikely in blockchain is because of the amount of computational power used to not only solve the hashing algorithm, but to essentially recreate the blockchain that many times. So now we're going to go into the practical implementations of blockchain within IoT. And essentially the goal is to fulfill what's called CIA, which is confidentiality, integrity, and availability. Confidentiality essentially protects the system against data interception and capture. Integrity makes sure the data is not altered by unauthorized users. And availability makes sure that the system is functioning properly and not being used for any other purposes besides what it's supposed to do. And in the paper by Manillo and Ochogrosso, which is Blockchain Mechanisms for IoT Security, Internet of Things, they create this pie chart where availability is created by the implementation of firewalls, confidentiality is supported by VPNs and data encryption, and integrity is supported by the blockchain implementation. Another paper called Blockchain for IoT Security and Management, Current Prospects, Challenges, and Future Directions, proposes that blockchain itself can cover all of CIA. It supports integrity because it's immutable and redundant. It supports availability because a denial of service attack is unlikely to succeed. And it's confidential because of the data encryption by a public key. What's holding IoT back from implementing the more classical implementation of blockchain seen in cryptocurrencies is that a lot of computational power is needed to create the proof of work. And most businesses find that cost impractical. So there has been research done to implement blockchain in IoT that is cost effective and practical. Which brings us to our next topic, which is blockchain implementations in IoT, for which I have two examples. One is smart homes, and the other one is intelligent transit systems, or ITS for short. So first we'll talk about smart homes. Currently, there are security vulnerabilities within smart homes. Smart homes generally revolve around a centralized gateway architecture, which has vulnerabilities where people are able to capture unencrypted passwords that are left on the network, and also DDoS attacks happen when one person corrupts one node and the node therefore sends bad information to the other nodes in the home. And when I say nodes, in this case, I mean things like refrigerators, thermostats, generally the IoTs that make up the smart home. So a proposed solution given in the paper below is what's called a lightweight blockchain. Lightweight blockchains are scaled back implementations of blockchains because they're on a private network, so you don't need a robust proof of work. So this implementation has 3 layers. The bottom layer is the device layer, which has the IoTs that generally scan for user data. And then you have the gateway, which essentially acts as the middleman between the device and the cloud layer. The gateway sends the data and the device ID to the cloud, while the gateway also sends data back to the users. In the cloud hosts an Ethereum blockchain. In this blockchain, the data, which in this case is the data sent from the devices, is copied onto multiple databases and checked against to detect possible forged blockchains. In this network, the device ID has to be uploaded periodically. So the paper describes the interactions between the layers. So starting from the top, first the gateway requests for the ID of the device, and that is sent to the device by an encrypted message, which has the public key to decrypt the message with. So the device with the public key decrypts the message and then sends the ID that's encrypted by a SHA-2 with a public key. The gateway then decrypts that ID and then verifies that the ID is in fact supposed to be on the network, and then it registers the ID on the cloud. And then the gateway requests the data from the device with the same encryption strategy. The device then decrypts the request and then sends the data back, so then the gateway then stores it on the blockchain. So the special features for this implementation is that, like I said before, the private network reduces the need for a proof of work while keeping the data encrypted in the blockchain. This implementation also protects against DDoS because the attacker can't continue indefinitely because of the resource limitations on blockchain. As well, for 51% attack to succeed, the attacker would need computing power greater than 50% in the network and create blocks faster than the network, creating forged ledgers. This is impossible because the number of the nodes in the network has to be greater than the sum of the hash computational power. So the next example is intelligent transportation systems, or ITS, and the current issues are kind of the same as that of the smart home, and the main issue is that the architecture is centralized, which creates a single point of failure. But another issue is that there's a lack of trust in third parties. So one example of ITS can be paying parking tickets. So you would have to send money to a third party, and then that third party would have to send money to the city. And this general lack of trust of third parties would keep users of the ITS from sending money. So this architecture is a little more layered. So there's 7 layers. So there's the physical layer, which has the devices, which can be also vehicles. Then there's the data layer, which is the actual blocks, the timestamps, and the hash functions. And then above that is the network layer, which is the peer-to-peer network. And then the consensus layer, which has the proof of work. The incentive layer specifies the economic reward in creating the blockchain. The contract layer, which has the smart contracts, which we'll talk more about in a minute. And then there's the application layer, which describes the general use for the service. So this interests me because this introduced the contract layer, which has the smart contracts. And smart contracts are immutable code that run on top of the blockchain that triggers a certain action once a condition is met. So this gets rid of the third party. You can use the concept of Kickstarter as an example. So in Kickstarter, you have a certain goal, and the goal has to be met in order for you to get the funds. But this is all determined by Kickstarter. With a smart contract, you can have a line of code that generally does all of this without the use of a third party. So all in all, I think blockchain is a very promising solution for security in the IoT space, as well as other spaces in general. One thing that I hope to see more of are more concrete examples. So the smart home was probably the most concrete example I gave, but the ITS example was a little more theoretical because to study this implementation in the ITS field, you would need an environment that really doesn't exist yet. And given that 5G is being more widely adopted and this would cause more use for IoT, I would hope to see more studies in the field. And one exciting possible study would be to see how this implementation can work within the supply chain. And here are my references, and thank you for listening.